So maybe we should just start out explain, like, what is LIGO?
LIGO is a huge project aimed at being able to take the bending of space that we think is happening all the time and turn it into some kind of signal that we can use and measure. And it's a transducer. It's like having a voltage meter or a microphone, but it's like a microphone for space.
Can you do the beginner's explanation of what it actually is, what the device actually is?
Yeah. So we think, or we now know, based upon the Einstein's relativity theory from 100 years ago, that there isn't a real force of gravity like there is a force between magnets or between charges or things like that. But instead, the way that gravity works is that it curves space. And so it's a lot like imagining what happens when you're jumping up and down on your bed and somebody else is jumping on their bed. I guess because if this happens to you all the time, then this is something you're familiar with. But whoever's heaviest makes a big impression in the bed, and then whoever is littler has to account for, what kind of an analogy is this? Whoever's littler has to account for the depression in the middle of the bed and adjust their jumping accordingly, and you tend to slide into the biggest dimple in the bed. So those who do trampolines or jumping up and down on their bed understand how, well-trained and understand how gravity works. So to detect this on the Earth is incredibly hard, and people have long ago measured the curvature of a space due to the Earth and due to the Moon and other planets and that sort of thing. And so we well understood that in fact space is curved, but we had no evidence to support the idea that the curvature of space could travel through space as waves. The detection of gravitational waves for decades had been debated in the scientific community. People thought it was just imaginary, that it was waves of thought, people called it, because they thought it was just waves of mathematics. It was just some equation you wrote down, but it didn't make any sense. It was just kind of a nonsense thing. And some decades ago, people realized it was real, and then some crazy people said, hey, let's try to measure this, even though it was millions of times like factors of millions not possible. But luckily, this is just something I'm not capable of, but through a combination of optimism and courage and not knowing the right answers to several equations, they were able to start up the field and start to look for these things. I think if they had known how tough it would be, or that it was going to take 55 years to have success, probably no one would have started. And so now here in the modern times, the way we do it is we use the tool of laser interferometry, which is, for those of you who are interferometer aficionados, it is a Michelson type interferometer with a lot of extra stuff added onto it. For those who are not, the concept is simple. It just has to do with interference. So you take a laser, like a laser pointer, but much more expensive and therefore much more stable.
Is it $1 billion now into the project?
Yeah.
Roughly?
Yeah. The laser itself is cheaper. You could do the whole thing with a $100,000 laser.
Oh, okay.
That's about the laser cost. You split it in two, and you send it in two separate directions. And then when the waves come back, they interfere with each other. And you look at differences in that interference to tell you the difference in how long it took for one beam to go one way and the other beam to go the other way.
Mm-hmm. And
so this, the way I said it was really careful there, because there's a lot of confusion about the idea of these are waves and space is bending and everything's shrinking and how come the light's not shrinking and so on. We don't really know. There's no real difference between the ideas of space and time warping. It could be space warping or time warping, but the only thing that we really know is what we measure, and that's the mantra of the true empirical person, I guess. We send out the light, and the light comes back and interferes, and the pattern changes, and that tells us something about effectively the delay that the light saw. And it could be that the space-time curved so that the light took longer to get there. But you could also imagine that there was a change in the time in one path as opposed to the other instead of the space. But it's a mixture of space and time, so it sort of depends on your viewpoint. But this warping of space-time is what's measured, and we turn it into a real signal by putting the interference of the two beams onto a usual photodetector that's like a solar cell that you would use, and so it turns light into electricity, and that's the whole thing.
And then you measure it by looking at waves.
Well, the whole measurement is right there in the electrical signal out of the photocell.
Okay. And so then how do you go about converting it to, I've seen a bunch of these like sounds of things you've measured. How do you go about that process?
Yeah, it's the same as like an electrical instrument. If you have an electric guitar, when you play whatever you're playing on there, it generates an electrical current in the pickup coils of the guitar. And that signal comes out through a little cable and goes into an amplifier. Mm-hmm. And then that's directly makes sound. And the same for us.
Okay.
So the photodetector detects a signal, which turns into electricity. And then we take that electricity and we drive a speaker, and then it makes sound.
Okay.
So there's no... I can understand what you're asking. That seems like a little weird. How is it that the wave from outer space can directly get turned into a signal in a speaker? It happens to be, and then I think this is a whole another topic to discuss. It happens to be that the waves that we're detecting and the waves which are easiest to detect are exactly in the human audio band. Mm. So the waves that you and I can hear with our ears, that's the whole frequency range for gravitational waves that we can detect. Gravitational waves happen at all frequencies, but they're really loud right in this band. And so our detectors are aimed for this band because we expected the audio band would be a good place. But our technology also happens to be only capable of detecting things in this band for a lot of technical reasons, which I can tell you about. That happens to be the case. And so it is a little weird, but the signals directly make sound.
Mm. So what I wanted to talk about then, I saw in one of your talks, I guess it was from last year, you were talking about creating new kinds of mirrors to focus, rather, the mirrors that you had created focused the vibrations to certain parts of the mirrors, but you were working on creating new mirrors to detect other things or different wavelengths.
Yeah, exactly.
Yeah.
When I first heard about it, it was I was going to say, when I first heard about it, I thought maybe it was unbelievable, but I have to say, I don't think when I first heard about this project, I don't think I understood enough to even understand that it was impossible. So I never went through this disbelief period. I just kind of slowly merged into it. But a lot of people with good reason say it's impossible to make these measurements. And the reason is, if you imagine zooming into where the black holes are in outer space, they're like a billion light years ago, a few billion light years ago, and the universe is only 13 billion years old. So it's a good fraction of the size of the known universe away. And if you get close to these black holes, the amount, as they're merging and eating each other, the amount that the space is warping is enough so that, like this water glass, it would be shattered, but it would be stretched if it was stretchable to, like this. It would be a huge stretching. But the wave, as it propagates to us, like waves do, they get attenuated. So imagine this stretching has a lot of energy in it, but as it spreads out, the amount of energy has to be conserved as it propagates. And so the amplitude of the wave as it comes to us gets reduced like 1 divided by the distance. And so the energy in the wave goes like 1 divided by the distance squared, like any other kind of radiation. We measure the amplitude instead of the power. Mm-hmm. We measure directly the stretch rather than the heat or something like that. So we're able to look a lot deeper into the universe than you would naively expect, because our signal only decays like 1 over the distance instead of the distance squared.
Okay.
So the wave comes to us, and by the time it gets to us, because it's billions of light years, the squeezing and stretching is much less than 500%. It's more like a part in 10 to the 21 or 22. So that means if you have the whole Earth, for example, is about 10,000 kilometers in size. And so that the whole Earth will be only stretching by about 1/100th of a micron, which is, I don't even know how to imagine that. What's a micron? A micron is like the wavelength of light.
Okay.
Or my hair is, the diameter of what little hair I have here is about 100 microns. So it's 10,000 times smaller than the width of this hair.
Is how much the entire Earth would stretch.
Yeah.
When it was hit with the gravitational wave that you initially measured.
Yeah.
Okay, which was a large one.
Which is a very large one. We've not seen anything of that size since then, since that first one. And so that's such a tiny distance. Our detectors are big. They're 4 kilometers, so they're not 10,000, unfortunately. If I was in charge, I would drill through the center of the Earth, and there would be mirrors. I would put a big L in the center of the Earth, and then there would be mirrors on both ends. And
that would be ideal.
That would be ideal, and that's what we would use. But I'm not yet in charge of everything.
But then, okay, so to divert a little bit, can you explain how the FabryPerot interferometer works? Like, because it's 4 kilometers, but it's also kind of like bounce back and forth at the same time, right?
Yeah.
So effectively, it's actually longer.
Yeah.
The laser travels a longer distance.
Yeah, that's right.
Okay.
So what's it like? It's the FabryPerot cavity means rather than just send the laser beam down, we send it into a thing which has 2 mirrors into it. And just like, I don't know if everybody does this, but when I was a kid, I wondered, here's this bathroom mirror, and what if, I can see my reflection, and then if I go into the fun house, like during Halloween, I can see multiple reflections. And what if you put 2 mirrors together and you set a flashlight and then you took it out? Would it bounce around infinity times and explode the mirrors? And, I've always tried to, I wondered about it. And it turns out, no, sadly, you cannot destroy the universe by facing 2 mirrors together.
One kid didn't figure it out.
Yeah. And the reason is because at each mirror surface, a little less than 100% of the light gets reflected back.
Right.
Some of it gets turned into heat or things like that. And so the FabryPerot optical resonator is just 2 mirrors facing each other. And one of them has a finite transmission. So it's set up so that, let's say, 1% of the light comes out and 99% goes in.
Mm-hmm.
Or, no, 99% gets reflected and 1% goes through. That's the 100%. And so when you set it up at first, you have these 2 mirrors, and you put in a beam from this side, let's say, and only a little bit gets in. And so that little bit gets in and starts bouncing around. But by the time it comes back, you're already putting in more laser light. You're constantly putting in more laser light.
Mm-hmm.
And that builds up constructively with the waves, electromagnetic waves you're sending in.
Mm-hmm.
And slowly, the power builds up in the system just through this little leakage. And it builds up until the point where the amount coming out is about the same as the amount going in.
Mm.
And at that point, you have, let's say, a few hundred times more laser power in this system than if you had just sent in a single beam. And that's not so challenging. It's easily doable. And it gives you basically a factor of 200 extra sensitivity than you would get.
So the extra power of the laser generates more sensitivity?
Yeah. It's just like you said it, though. It's effectively like the laser bounces a bunch of time.
Okay.
And so you can imagine here's this space-time which is curved. So now the laser has to travel through this curved path. And so it's a little bit longer of a distance. And when it goes down and comes back, it picks up a little bit of extra phase shift. It's just a delay. And now that's through one round trip. And if you do 200 round trips, you get 200 times the phase shift. And so that's what we do.
But does that net out 200 times the noise as well?
Yeah.
It does.
Yeah,
okay.
Exactly. So the more times you go around, and the more you pick up the signal from the mirror motion.
Yeah.
And so the signal to noise, trying to get below the fluctuations of the mirror, don't actually get better by building up more power in the system. And in fact, if it can even go the wrong way. At some level, at some point, the quantum mechanical fluctuations in the number of photons that are in your system becomes so large that the mirrors are shaking. And so the more power you have, it just gets worse. And so there's a limit to how much power you want to put in there before you get into trouble.
Okay.
But so you might reasonably ask, why do you do it then if it doesn't help? It helps. It helps just in building up the signal. And if you're limited by the fluctuations of the mirror motion due to the environment or something like that, then more power is not any good. But most of the time, in most cases, when people are doing precise measurements with lasers, they're limited not by the mirror motion, but by the noise due to the fact that they have a finite number of laser photons. So if you just take a laser and put it onto a photocell and you listen to it with your speakers, which you can do, it sounds kind of like a hiss. And that hiss is because quantum mechanically, the energy of the light is sort of is in the discrete packets, which we call photons. And so if you have a 1 watt laser or something like that, you have many billions and billions of photons, but you end up with a hiss level of noise due to basically the quantum nature of the light that you can't get beyond. And increasing the laser power builds up your signal. So if you double the laser power, you double your signal, but your noise due to these random photon fluctuations only goes up like the square root of that power.
Oh, okay.
So you win a little bit for that particular noise.
And why not just have a super powerful laser?
We do have super powerful lasers.
Okay. But you need it to be even stronger.
Yeah. It is tough to build a super powerful laser. I'm trying to think of how to put this in context. So the people who have worked with these lasers will understand why we do it this way. If you have these days, like if you have $50,000 in your pocket, you can go onto the internet and buy yourself a scientific research grade laser that's a couple of watts and will work fine for you. And we end up with a 200 watt laser, and there's no such, you can't buy anything like that these days. You can buy lasers that have that much power, but their frequency is not very stable. And our laser is used as the meter stick for doing the measurement. It's like each wave of the laser is one tick on a meter stick. And if you have an unstable laser, that means these little waves, instead of being very precise, are jiggling all over the place. And so your meter stick, it would be like having a meter stick where the tick marks are kind of dancing around.
Right.
You can't use it to measure anything.
Right. And it's so precise because, like, just so I don't mistake it, the first, the two black hole measurement, how much did it move?
About 10 to the minus 18 meters, which means 1/billionth of about the size of an atom. It's small.
So yeah, you can't do that.
You can't do that. So you have to, there's no laser in the world which is good enough to measure this. And so we take the best laser in the world that we can find, and then we stabilize it and make it about 10 million times more stable than what you can buy. And then it's kind of just barely good enough. And we're going to have to do better if we want to do better. Yeah.
So maybe that makes sense to, like, what changed between LIGO and advanced LIGO? Was it a shift in the machining, or what did you do?
We got a bunch of new, younger people who are really smart. That is by far the biggest effect. And because they were, like miraculously, they showed up just at the right time, in this, they showed up for graduate school in like 2010 or 2011, right when we happened to need them.
Yeah.
Without knowing about the timing, they just showed up.
Yeah.
And they finished some classes, and then they decided to ship out, and live at these remote
Louisiana
sites in Louisiana and Washington.
Yeah.
And they just figured it all out. They just, day in and day out, they just figured out every problem and solved it.
And so what are some concrete examples?
I mean, there were some engineering changes in going into this new detector, which was 10 times more powerful laser, and we isolated the mirrors a lot better from the environment, and the mirrors are much higher quality. They're super beautiful and much heavier and really good. So there's a bunch of these technical things which were changed.
Yeah.
And each one of them on their own worked really well because the engineers who were constructing them did a great job. The problem was when trying to put it all together, and these things just never reveal themselves when you're sitting in a little room and designing your widget. But you put it in a suitcase and carry it on the airplane and try to bolt it onto the 4-kilometer $1 billion machine, and then it's just like total disaster.
Well, because when I first heard you talk, you were talking about like deer getting close to the tube and all these things. And how do you isolate?
These things just don't matter at all. Here in our labs at Caltech, you measure one thing or two things, but the full problem of putting it all together, and what's the problem? That only shows up when you have hundreds of kilowatts of laser power and giant mirrors, and it's all running together. For example, I would say, it's still one of the toughest problems, and it's not completely solved, is it has to do with the interaction between the laser beam and the mirrors. And normally, when you think about these things, you say, well, the laser beam goes out there and it bounces off that thing and it comes back, and that's all there is to it. And maybe the mirror is shaking around, so that's a problem. But in fact, there's so much laser power that it's weird to think about, but there's so much laser power when we hit the mirror, it moves the mirror. Yeah. And the mirror, to imagine it, is about this big.
Mm-hmm.
And it is 40 kilograms, which is like 100 pounds?
80 something, but yeah.
Anyway, some number of pounds. Who knows what pounds mean? It's 40 kilograms, which is heavy. It's like a little person. And in the previous LIGO 20 years ago, I would just pick up a mirror and you could carry it in and put it in. But there's no longer any of this, like, I'll pick this thing up and carry it around.
Bring it over in your truck.
Yeah, it's way too expensive and way too heavy. But this super heavy thing, we're hanging from handmade glass fibers, which are super thin, and it's sitting there and swaying around. And when the laser power hits it, it just moves. And even more annoyingly, when the mirror moves a little bit like this, the laser beam at the other end, 4 kilometers away, it moves. And so then that mirror twists a little bit like this. And now the reflected beam moves a little bit. And these two things are talking to each other through the pressure from the radiation, the laser light.
Right.
And that's super annoying, and it's not a thing that you can test if you're in a tabletop. You have to put the whole thing together. You can simulate it and calculate it, as we did.
Right.
But when you put it together, it's a lot more trouble than expected. And that took a long time to solve. It's still not solved.
Yeah.
It kind of works, but when we start increasing the laser power, a lot of these interactions happen which are really troublesome. And luckily, we have a fresh stream of new people coming into grad school.
Yeah.
And if they, we hope they remain as good as the people we've had so far. If that doesn't work out, we're in trouble.
Yeah. So what do you suspect will be the changes that suspend the mirrors in a way that the laser doesn't move them?
Oh, they're just going to. I don't think we have any way of doing it. What we're doing right now, we have just a sophisticated feedback control system that we measure the light beams which leak out of the system at a bunch of places. Uh-huh. We detect it, and then we have a system of something like 20 feedback loops, which puts forces on the mirrors to try to keep it aligned and keep this from being such a problem. The trouble is, we're trying to detect gravitational waves, which are tiny. And so when you do something, you imagine like this, let's imagine like this is the mirror, and this little that there's this little ting, which is about how long the gravitational wave lasts, like this. And now we're trying to control the pointing of this thing because it's getting steered on by the beam, and so I have my feedback control like this, trying to hold it on. But you can't do this if you're just
throws the whole thing.
Yeah, it just screws up the whole thing if you're applying too much feedback because you mask the signal that you're trying to detect.
Right.
And so we're in a place where we would like to figure out how to better optimize our feedback controls so that they don't mask the gravitational wave signal so much. And luckily, there is a community which thinks about how to optimize control systems, and they've been a great help to us. But we're now at the limit. I don't know. We're at the limit of what I understand, and so I'm looking for someone who knows more than me to help us improve this situation better. And I hope some of our modern learning techniques and signal processing techniques can be used for this.
Well, yeah, I mean, I want to talk to you about that as well. Like, what techniques are you applying right now to the data, and what do you hope to apply in the future?
Yeah, there's a whole menu of things. We basically, everything that we can find, we just read a lot of things on the internet, and everything that sounds clever, we want to use it. So since 10 years ago or more, we have been trying every single kind of linear subtraction. So we have, I don't know, let's say tens of thousands of sensors which are measuring the environment and the movement and the motion and these feedback controls and all kinds of things like this. And we take each one of those and we compute the optimal Wiener filter, which is that's the optimal filter that you can apply to the sensor signal and subtract it from the data. And so we use it. In some cases, we calculate the filter and then directly drive the mirrors so that in hardware we remove the noise before it's actually made. So we do that with a lot of things. And so we remove, by about a factor of 100, some large noise sources that way in the hardware. And we do it in the hardware because they would mix in some sort of nonlinear way back into the data. So it's better to clean up the data in the hardware in the analog because there's no dynamic range limit in analog. There's no number of bits, more or less. It's atoms. So there's a lot of bits. Once we get into the data, there's still more we can do. So we do some more linear subtraction of noise, and we're able to improve the data a little bit by factors of a few.
Okay.
But now we've reached the limit of what you can do with linear noise subtraction. And we need some better ideas on how to do the next thing. And the next thing involves nonlinear regression. So one of the things I'm working on right now is how to take basically a huge data set. Depends who you're talking to. When you say huge data set, it doesn't really... Huge data set for me, but not a huge data set for a lot of other people, I guess. We have thousands of signals which are 16-bit and recorded at 16 kilohertz. And some of these signals, not all of them, will combine in via some sort of nonlinear function and show up in our main data stream where we like to look for the gravitational waves. So for example, it might be like the cosine of one signal times another signal plus another signal, and then that whole thing squared or cubed or something like that. So it's not super strange. So it's the kind of thing you can imagine doing on a laptop. But it's a little tough to search through the full space of sensors, and so we just haven't done it yet. But I think a lot of the things that are masking the lowest frequency gravitational waves, which come from the biggest black holes, that data can be cleaned up quite a lot if we were to come up with better techniques for doing it. And I think it's all doable. I personally haven't found the algorithm to do it, but we're working on it.
Because there have been 3 now in the past handful of years, right?
Right. There was one in September 15th of 2015. And then there was one on Christmas Day of that year in the evening around 9 o'clock. And then for almost a year, we shut down to improve a lot of things in our detector.
Wow.
From most of 2016, basically.
Okay.
And then we turned back on November, December of last year.
Mm-hmm.
And then we had another detection in January.
But do you suspect there have been many more that you just can't parse?
Yeah. And I think in our data, there must be, probably we could double the number of signals we have right now if we were to, I mean, that's my guess. It could be much more.
Okay.
And the reason is, if you imagine, this is my only prop. So I'm going to use, this works for everything. So if you imagine this lip is a black hole here. When I do this, if I can hold it right. No, let me hold this part. All right, this is not cooperating. Yeah, there you go. It rings a little bit. And that ringing frequency has to do with something complicated about the vibrations of this thing and the water that's in it. The black hole, however, is a really, really simple animal. The mathematics are really complicated, or it depends who you ask.
It's pretty complicated.
Yeah. I would say it's really simple. It's more challenging. This is about as challenging as the mathematics for the black hole. The physics are stranger, but complicated things are complicated. Anyway, a black hole that's just sitting there and not spinning, you can easily compute the frequency at which it rings. Mm-hmm. And it has to do with the amount of time it takes light to travel around the border. So once you know the size of the black hole, if you're looking at it, or if you know its mass, you can compute the frequency at which it's going to ring. So it's sitting here, and let's imagine I throw like this glass into the black hole. As this glass gets really close to it, the black hole horizon will be perturbed a little bit like this as it swallows this new piece of mass. And then that perturbation immediately settles down, and there's a little wave that travels around the edge of the black hole. And then that gets radiated out. And that radiation is what we detect. So when the two big black holes merge together, the same thing happens. They form a bigger black hole. But now, since the thing's bigger, the frequency of the ringing will be bigger. Just like if I made this cup 2 times bigger, this frequency would be 2 times lower. So the bigger something is, the resonant frequency is lower.
Okay.
So the biggest black holes we can't find right now because this kind of technical noise, feedback, and the vibrations from the environment are bigger than the fundamental quantum physics limits of measurement. And that all of that data is being measured by other sensors, microphones and things like that. So it's a data science job right now to figure out how to take thousands of standard sensors that you can buy off the shelf, and mix that data somehow with the gravitational wave data stream in a smart way that removes this kind of foreground noise and allows you to find the deeper signals.
But it's all modeled. Because that's what I was wondering.
It's unmodeled.
Yeah. Because when I saw the first announcement of the 2 black holes, I was wondering like, oh, have they just been looking for this pattern of waves, or this pattern the whole time? And so that you kind of have like a guidebook, like, okay, if we see this, it means that.
There's a bunch of different variables which characterize the black holes. I made it sound simple, but they can be spinning, and depending on their orbits and that sort of thing. There's a lot of parameters, maybe several parameters that go into it.
Okay.
But in the end, it's just some parameters. So we might have a 5 or 10 dimensional waveform space that we search through, but it is just a big catalog of waveforms, little wavelet looking things. And so for all the signals that can possibly come from black holes, we think we can search for them just by comparing with a known template.
Really? And so that's just the wavelength and the amplitude? That was...
well, the frequency evolves as the signal comes in. So when they're far away, when they're first born, maybe they're 1 million years before merging. And so they're far apart and they just spin together like this. And as they get closer, eventually there's a little whoop, and then they pop together. But we know what that frequency evolution is based on their masses and how they start.
And so then do you think in addition to, paying more attention to all the other measurements that you're doing, there's going to be a hardware innovation. Like what happens next?
Yeah, I think, hopefully someone will watch this podcast and then say, have I got the solution for you? And I'll just get a piece of, someone will send me a link to their GitHub, and then I will have the whole answer.
Over. Yeah.
And then we'll break this thing wide open this year or next year.
Yeah.
And then we'll be back more at the fundamental limits. So you asked before about this new mirrors, that sort of thing. And again, using the universal prop here. So with this, if I do it, so that rings for about a second, and that has a frequency of 500 hertz. And so that means the energy stays pretty well localized in the vibration of the glass and doesn't go someplace else.
Mm-hmm.
And this is, I don't even think mine. This is something I found in this hallway.
Right.
But it's an okay piece of glass, but it's not meant for any, I don't know, it's not meant for scientific purposes. And the mirrors we have are more like, they store the energy better, something like about 10,000 times longer. So if I were to ping one of those would last for, hours. They would just keep ringing and ringing. And that has to do with that tells you a little bit about how well you can measure the motion of that mirror using lasers. Mm-hmm. And the reason for it is because of the motion of the atoms and the thermal energy in the system. Mm-hmm. So when you come down to it, if you've removed every other noise from the outside world and you just have a thing sitting there, mm-hmm. Because it's sitting at a finite temperature, its molecules are bouncing around like this and it's shaking. And that's just sort of a thermodynamic limit that you can't get past. Mm-hmm. But the question is there a pattern to the way that they're moving, or are they just moving randomly? Mm. And if you have something like this, dumpy old glass, it's pretty much moving randomly, except for there will be a lot of energy in the different harmonics and tones that you can make. So if you measured this thing, you would notice that there would be a lot of oscillations that had a certain frequency.
So is that how you can measure something? Actually, rather, the laser is also affected by the gravitational wave.
It is, yeah.
Right.
Yeah.
So is the resonance of the mirror, that's the reason why you can measure it? Because you can shoot it after and it's still resonating and you pick it up?
No, it's just that we just ignore the frequencies at which the mirror resonates. So the mirror resonates at a few specific tones, like you can think about it like waves on a string. If you have a guitar or violin, depending upon how you fret it, I don't understand violins. Anyway, instruments with frets, I understand.
Sure.
So depending on where you fret a guitar string, it plays a different tone. And it just has to do with the length of the wire and the tension. Mm-hmm. And the same for the mirror. The mirror depends on something like how heavy it is and how fast sound travels with the mirror. And so if you have a mirror that's really, really pure, then all of that thermodynamic energy is focused at just a few frequencies. And so it's just sitting there, and if you shoot it with a laser or with a very expensive system, you can hear the thermodynamic vibrations of the molecules in the mirror. And in fact, that's what we hear most of the time. Mm. And so if you listen to the LIGO data stream, there are these high frequency ringing going on all the time. And it's all the mirrors just constantly vibrating thermally.
And so, okay.
So we just don't look for gravitational waves at those very specific frequencies, but they're very narrow. So it's just like doing the removal of like the power line harmonics.
Yep.
We have all of that, so we have to remove it. So if you have a hum filter, as you do when you record music, for example, you do the same thing. So we have hum filters that remove all the lines that are happening.
Well, it's kind of like why you're measuring everything, right? Because you're just like, if you can detect it, then you take it out. That's therefore not a gravitational wave.
Yeah.
And so do you suspect that you're picking up anything that you can't even define right now? Or like, are you lumping things in as gravitational waves that might not even be?
I don't think
that's unlikely.
That's unlikely. I mean, it's always a worry.
Yeah.
We're really paranoid about that kind of thing because you just hate to be like the boy who cried wolf. Say, I have a gravitational wave, and then you find out 6 months later that it's just a misbehaving refrigerator that was located
We
close
bought
to
the same fridge in Louisiana and Washington.
That's right. I'm sure we did. I'm sure there's something going on like that. And so those problems we've been finding for decades. Things like we bought the same electronics board from the same manufacturer, and it has a crystal that happens to radiate at a certain frequency, and those two things are kind of synchronous at two different places. And once in a while, you'll get like 3 crystals beating with each other, which will produce something in the audio band. And there's thousands of stories like that, which we all forget because you do it, you find it, and then you take the thing out and you smash it with a hammer. And you go have a party because you found some terrible thing.
Do you have like a wiki of known bugs? Just like chronicling all this stuff?
No. Yeah, I think it's just stories.
Okay.
It's mostly stories.
Because that's like most of the job, it sounds like.
Yeah, it is. It is.
You just like find a new thing, get rid of it.
All the time. All the time. That is all. And it's gotten to the point where we all feel like we're telling UFO stories because we've already found all the easy things years ago. And now the things that are limiting us are the weirdest mechanisms. And you come back, you spend a day, like working late, it's like 2 a.m. And then everybody kind of comes back together and they're like, what happened? What'd you find? And then you start telling this crazy story. And you say, it seems like if I stand in this part of the room and then she stands over there, and then we turn the mirror like this kind of hooting, screeching noise happens. And everyone's like, you're crazy. There's no science in that. It sounds like a superstition.
Yeah.
Like, I don't know what to tell you. It's 2 a.m. We've been working on this all day, but this is what happens. And then we say, all right, let's go get some sleep and think about this. And all the problems are of that sort now.
Okay.
But luckily, we have people who are obsessed about these kinds of problems, and they're going at it and finding them and solving them. And this summer, or last summer, we found another one of these problems that's like, it reminds me of some kind of sci-fi horror movie. Trying to think of what it is. It's like there's this really bad movies from the 80s called They Live.
I haven't seen it.
Yeah, they have 2 professional wrestlers, I think, are the actors in it. Anyway, it's terribly bad. But at one point, one of the guys says, like, you need to put on these glasses because if you put on these glasses, you can see who the aliens are. They mostly look like people when you put them on.
Yeah. Okay.
And so the guy puts it on, and then he starts looking around. It's like all of his friends and everybody he knows, just like he doesn't want to know. It's too much. And we found a problem like that last year, which is that the light which bounces off of our mirrors mostly keeps going back and forth in these optical resonators that we have. But something like a few parts per million of the light shoots off in some other direction. Mm-hmm. And then it shoots off, hits some unknown thing, and then some few parts per million comes back and then interferes with the main system. And so then it's something like, there's basically an infinity, it's like a disco ball. You can imagine like a disco ball is lit and then the light beams go everywhere. That's an extreme case, but at the part per million level, our mirrors, as wonderful as they are acting like disco balls. And so little bits of light are heading off in all directions. And when the light comes back from those places, it has picked up a little bit of the vibration from whatever thing it hit. Mm-hmm. And so finally, at some level, we're measuring the acoustical vibrations of the entire 8 kilometers of metal tubing of our system. Because there's a little bit of light hitting those things and coming back. And then, now what?
Yeah, I mean, that's kind of like the rub of you create these like perfect sealed systems, but now it's sealed.
Yeah.
And so you just throw a marble around and it's just going.
Yeah, it just keeps going.
And
we've got to take care of it. So we've been here at Caltech and also at MIT, we've been thinking about what to do about this. And so we've come up with some designs on what to do, and basically we've taken some of these substances, which are the blackest, darkest things you've ever seen, and we're going to put them in our system to block these places where the light beam goes. So
how do you put it? Yeah.
We're going to open up the vacuum system and walk inside. We're going to put on full clean room suits and then walk inside and put these things in.
Where?
All over. Every place that we can find. I never want to see this again.
What kind of substance is it? I don't fully understand.
Well, like my shirt before washing was very black.
Yeah.
Now it's kind of gray.
Yeah.
But what you mean? Are you asking why are things black?
No, I'm
that's
not.
A good question.
You can answer that though.
Yeah.
No, it's like Spinal Tap.
No, it's an honest scientific question.
No, is it like a paint that you're putting on stuff? That's what I'm asking.
It's a bunch of different. So each. These are the kinds of trivia questions that I know, and then I wonder why. What have I done with my life that I know the answer to these things? In the array of different blackening things. There are the things that you think are black, which are black sort of to your eye, but then you shoot a huge laser at it and you use a really sensitive detector to sense it, and then you find out it's not so black, it's really gray. And so there's a bunch of garbage you can buy online which says that it's the best blah, 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 blah. Most of it's junk. So we have a couple of engineers in a building over here who have been exhaustively and carefully looking at every single thing that is promised to be black on the internet, and then it's like a Mythbusters episode over there.
Yeah,
and they finally have come down to a few different solutions, and so some of them are. I don't think I could accurately describe all of them, but some of them are black, like it's basically glass like this, but like colored glass, like I'm missing the word for it. They have it in churches. What do you call it?
Oh, stained glass.
Stained glass.
Yeah.
So you have glass, and then when you're making the glass, you put some other stuff in it, and it comes out a different color, right? And so you can, I don't know what I'm doing. I'm sure they don't do this.
Sprinkle it in.
But I don't know make glass, so I don't understand. But I imagine it's like this. You have this molten glass, and then you pick up...
It's like food coloring.
Magic pixie dust,
yeah.
And you put in some stuff, and it's perfectly absorptive for the wavelength of the laser you're looking that you care about. So,
gotcha.
Red stained glass, for instance, lets through red light, but it absorbs green. So red stained glass is really good if you have a green laser.
Mm-hmm.
We have an infrared laser, which is, if you imagine this is the whole rainbow from purple, violet to red, then our laser is sort of over here. So it's, anyway, imagine the rainbow, and there it is. It has a wavelength of 1 micron.
Mm-hmm.
And so for it, some of the things that look black don't work. But if you have a special kind of welder's glass, it really works. Welder's glass is good at absorbing pretty much everything with a longer wavelength than green.
Mm.
So that's one of the best materials to use for blackening. And then you can also get these so-called nanotube things like Vanta Black. I don't remember all the various black names, but they're all trademarked.
Okay.
So there's a bunch of stuff, which is essentially, you know how you can get lost in a forest? It's like that for light beams also. So if you take a thing and you put a bunch of spaghetti-looking nanotube things, then the light goes in and bounces around like 100 million times before coming out.
Oh, okay.
And so it loses all of its energy.
Gotcha. Okay. And so then do you also expect like you're going to build more interferometers that are longer?
Yeah.
To clean it up?
Oh, to clean it up.
Or in general, like, do you suspect that like the next version is 8 kilometers?
That's an answer I don't really know, but
okay.
It is a good question. That's a really interesting question about if longer will clean it up. I'll have to get back to you on that. That's probably a few days of computing for me. Yeah, indeed. If we make the interferometers longer, like 10 times longer,
yeah,
that's dramatically good. I mean, it will cost a lot of money,
mm-hmm.
but that would take us from being able to measure things which are sort of, I would say, with the current systems, as big as they are, if we put in like our best technical hacks into them that we can imagine, we could maybe get to the place where the universe was about 1/5 or 1/6 of its current age. So we could look back something like 10 billion years into the past, which is pretty great. But if we built systems which were 10 times bigger, it's hard to do anything better than just make the system bigger. So the bigger you make it, the bigger the signal gets. And a lot of people have thought about the idea of making a 40-kilometer system, which you can put. There are several places in the U.S., for example, which have...
Each arm is 40K?
Yeah. So big open spaces, which are unused. And if we could find a place like that and get the funding to build something like that, it would be traumatic. Not traumatic. I hope not traumatic. Dramatic.
We'll see if the laser gets out.
Yeah. It would be dramatic. It would be wonderful. We would be able to find signals from basically all the way back. I mean, they would have...
Really?
Yeah. We would find the first stars in the universe and when they were collapsing, if they exist, which I think they do. But it would be so dramatic, we'd be able to measure things like how did space-time evolve from those early times? And did the universe start from different number of spatial dimensions and sort of unpack as it expanded and become three-dimensional? Did it start different? And did it go through a phase where it, like an extra dimension came up and then collapsed again? And who knows? We'd also like to know, does gravity travel through the three-dimensional space, or is it something like there's another spatial dimension which only gravity can see? And so something from that far back into the universe may have... I don't know how to draw this. I don't think this...
The cup can't do it.
The cup...
You have to dump the water out of the cup.
The cup can do it. The cup can do it. Watch this. So imagine that we're living on the surface of this cup.
Sure.
And this is effectively like our three-dimensional universe.
Sure.
Now, if I empty the cup, then when I go like this, the signal has to travel around the border of the cup. But because there's water inside, when I go down here, some of the vibration gets into the water and comes out this other side. And so there's sort of this boundary on which we're used to everything taking place, which is the three dimensions that we're familiar with. But there could be a fourth dimension, which is something like this bulk, the inner part. And in that dimension, gravity could travel faster. So it'll look like it's going faster than the speed of light. But that kind of stuff...
This is kind of blowing my mind. Yeah, I'm trying to figure it out.
It sounds like...
Yeah.
It sounds like there's just a crazy person who you found on the streets who's just telling you stuff about other dimensions.
Just think about it, man. 10 billion years ago, man.
10 billion years ago, there's other dimensions, and they're half dimensions, and maybe we unfolded from a flower. It's all on the table. I'll tell you, in the late 90s, when I was starting grad school, everything felt like it was pretty much wrapped up. The word on the street was like, well, thanks for showing up, but we've got this all wrapped up now, and everything makes sense, and the universe is exactly like we predicted it. We have a few loose ends to tie up. And this is the same thing that people were saying in the late 1890s also. They said, we got it all. We figured it out. We got magnets. We've got electric fields.
Got a telescope.
That's all there is. There's nothing else out there. And then there was this weird quantum thing that people... there was some data, but they were like, that's not real. That's just some nonsense. It's going to go away. And we're back into that period now where everything's back on the table. The universe is so strange and so far inexplicable that if you have got an idea that's a crazy idea, then your crazy idea is just as good as my crazy idea.
Yeah.
And let's put it to a test. If it's a hypothesis which is testable, we ought to test it.
So then, does it make sense to build an interferometer in space, like people have been talking about?
Yeah, of course.
I know it sounds cool.
Yeah, that's a plus. That's a plus that it sounds cool. It makes sense for a lot of reasons, I would say. On the ground, kind of we're limited to measure things that are that have a signal frequency which is more than 5 or 10 hertz or something like that. So we can go a little bit below the human audio band, but not much. And the reason for that is that the Earth is just vibrating all the time. And you talked about these animals before. The animals are going to be a problem. The clouds are a problem. I mean, eventually the gravity from the clouds and the gravity from beavers and hummingbirds and whatever. I mean, who knows what's out there? But you can Washington State, there's not a lot of animals out there, but there's tumbleweed, and those things are fierce. if you have never been chased by a tumbleweed mini tornado, then you're lucky. I don't know. And in Louisiana, there's a lot of animals, and you could build bigger buildings, but eventually the gravity from the gravitational fluctuations from the dirt and from the air, clouds. I mean, eventually it's just too much gravity fluctuation on the Earth. We just can't get past it. So we can remove every other kind of noise, but we can't go putting vibration sensors in all the clouds or something like that. That's kind of
not yet.
We're getting to the Baron Munchausen kind of crazy level. So we could go to the moon, but the moon's not all that quiet, and the near Earth orbit is not really that good for vibrations, and it's not a place you want to put a stable system. So to have a space interferometer, it's got to be on a far out kind of orbit that you can get to with things like SpaceX Falcon Heavy. And so there's a project called LISA, which is aimed to launch in 17 years from now. And that will put a system, a triangular interferometer in space, which is several interferometers. And that will measure gravitational waves at around 1 millihertz. So super low frequency. But those, at that level, there's almost no vibration out there. And they should be able to measure things all over the universe in super, super hi-fi. So we're measuring things with a signal-to-noise ratio of tens, and we hope to get to signal-to-noise ratios of thousands, which is really good. But they would be hundreds of times better than that. And it would be like... it's one of the... If you're a real connoisseur of violin or cello or some of these things, different musicians have a different finger signature a little bit. So when they're playing, you can hear things like the way that their finger moves on the bow, or the way that their finger moves on the string. Like a little bit of the friction. So you can hear these little,
like it's
tiny
slide.
Yeah,
a little bit. Yeah,
a little bit of the slide. But you hear these little things which change the character of the music. And if you leave one of these instruments sitting for too long, the sound, like some of these instruments like to be played. They warm up a little bit, the wood warms up, and then it becomes more like a warm instrument. And if you listen to it on, I don't know, like a 80s cassette deck with a Walkman, you're never going to hear that stuff. You need to have a full hi-fi system and some good cans, and then you really you feel it, you hear it. You need. These are kind of the things in the live performance that you'll never get otherwise. I've been to the Berlin Philharmonic, and that's what I'm talking about.
Spot.
If you want to understand about why we need better gravitational wave detectors, you go and you sit there in like row 5 or 10.
Yeah.
And these are some of the best musicians in the world, and they'll play pieces that but you've never heard like that and there's no recording that's ever going to do it, because you feel it in your chest, and you feel it all over your body, the sound, and it's a kind of richness that there's no way to record. And that's the kind of feeling that we want to get from what's happening out in space. And for that, we need an exquisite hi-fi system to get these little things. And it's not just for the pleasure of, oh, look, that black hole did exactly what we predicted. It's more for, we'd like to find out where the laws of physics break down and where something new pops up. If we want to find out other extra dimensions and new kinds of particles, and is space and time really just a illusion, and that there's really microscopic graininess to empty space and these weird kind of things.
So that's kind of the underlying question, because I mean, you'd said so many reasons before, but I wondered what the pitch was in the beginning, like why do this? And like, obviously it's, quest for knowledge, which is great.
Yeah.
But like, were those the concrete answers that people gave? Like, why are you doing this? Why make it bigger? What do you do?
Yeah, I think for everybody, there's a different reason for it. There's a whole spectrum of reasons. So, I always tell people the thing that I'm most interested in, which is, I think gravity, we've never been able to use it as a real probe of what's going on in the universe. What's the universe made out of? What is all this stuff? Why is space empty? Why is space so stiff? And why are there quantum fluctuations in empty space? And how come the universe ended up looking the way it does? Why are the galaxies so far apart? And how come there are galaxies? Why don't we just have a bunch of planets? Or
just floating around.
Yeah. How come planets are smaller than, it's like an endless number of questions about the whole, not really the stuff in our universe, but the structure of everything. And why did it end up like this? It could have been any number of things. And then we don't even know what space is made out of. What's empty space? It sounds like a question that's stupid and doesn't have any meaning to it. But, if you're, I don't know, imagine like two sturgeon floating around in the water. They're like 100 years old and they've gotten used to it. They don't really ask anymore, what is water? But, we know we can take it out and look at it in a microscope, and it's got flagellums and all kinds of stuff, and it's made out of H2O, which we can study, and it has a real microscopic character, which is important, and we need to understand it. And for those fish, it doesn't really matter. It just seems like a continuum. It's just everything is that stuff. But there is a whole deep structure to it, and space may be like that. It's just this whole, it's like opening the curtain on the real universe and what's really going on. What is the structure that we're living on? It could just be this weird framework that we've never imagined. And asking, and then you can, I think a totally legitimate question is, so what? And let's say you find, we've revealed the true structure of space-time, and there's a bunch of leprechauns down there building space, or who knows what, some crazy thing.
Just black paint.
And then, and then so what? What does that do for me? Is that going to relieve the traffic in LA?
Yeah.
No, probably not. So really, it's a curiosity-driven research. We're trying to figure out how to find out, reveal the unknown and what's going on. And these big science projects are really expensive. And a lot of people are involved, and they work at it, and then you really wonder, so what? They found out stuff like there's this particle or not that particle, or this star did something 1 billion years before, it's 6 billion years old, not 5 billion or whatever. But I think if that really was all that there is to it, you could certainly make the legitimate argument that, look, our society has got a lot of problems that we need to solve, and then how much of our resources are we going to put into pure curiosity-driven basic research, which doesn't have any kind of finite timeline payoff? And we got real things we want to solve here. There's people going hungry. What are we going to do? And I would say to that, when you look at the history in the last 100 years, and why has wealth increased and standards of living increased all over the world? And the reason for it is that people have been investing a lot in basic science for hundreds of years. And the reason that the U.S. became the leader in this is the government said, soon after World War II, that we got to be serious and put our money into this, because there is really a huge payoff, and we don't really care what you're researching. Just do something. Find something that excites you and do it really well. And if you're interested in engineering and science and technology, we are going to support that, because we've shown decade after decade that it's a huge hugely profitable payoff investment-wise. It pays off in gadgets and learning and wealth for the country in the long term, and it never fails. So you'll always have, you'll always be funding something which turns out to be a dumb idea, and then, okay, so it doesn't work out. But, to find a really great idea, you might have to test out 99 dumb ideas, and you might not understand why they're bad until you do it.
Yeah. But relative to the outcome, I think it makes a lot of sense. Cool. Yeah. I think we have a couple questions from Twitter, so we can transition into those.
Fantastic.
Get those ones.
I love Twitter.
All right. Dennis Thornton asks, what would happen to Earth if there was a black hole merger closer to home than the 3 detected? Say where Sagittarius A star is now.
That's not close enough to really do anything to us, but you can imagine it being even closer. So let's see. If it's too close, it just eats the Earth, and that's not interesting. We're just dead. But there's some range of distances at which other things could happen. So you could imagine, for example, it being out by, I'd say like at the next star system, like Alpha Centauri or something like that. And so we can compute it. Like the ones we detected were at, let's say, several 100 million light years, and Alpha Centauri is only 4 light years, I believe. So it would be stronger by that factor of 100 million, and which sounds like a lot. It is a lot, but that means that motion of 10 to the minus 18 meters would have been 10 to the minus 10 meters, which for us would have been like a hardware destroying level of signal.
Really?
Yeah, we would have just had electronics overload and saturate, and we would have just ignored it because we would say it's way too strong.
The levels are too much. Yeah.
It can't be right. But it would not have done anything like disrupt the tides or knock the moon out of orbit or anything like that. It would have to be extremely close for something like that.
Right. And so close that we might even already...
We would see it with our optical telescopes.
Really?
For sure. Okay. For it to hurt us.
Yeah. And it also would have happened already, right?
Yeah. Well, you could imagine, I'm trying to think of all the nightmare disaster scenarios. So let's say a pair of black holes gets formed in some weird 3-way encounter in a nearby cluster, and then it gets shot out, and it's traveling at like a million meters per second. So it's like a 1% the speed of light, and it's shooting at us, and it's coming at us from some strange direction so that we don't see it because it's occluded by something else. I don't know what that would be.
Sure.
Something. I can't simulate the whole solar system in my head, so I couldn't figure out the answer to this. But let's say it's coming from out of the plane, and then eventually we see it. It's like occluding some stars.
Right.
And so I'm thinking of this Hollywood movie that we would make based on this idea. So it's coming to us, and the binary is doing this as it's traveling, and as it's it's going to merge right when it hits this solar system somehow. And I don't know what we would do to stop this.
Yeah.
I don't know what that would be, but it could, I mean, we could compute something like that. And then that thing would really be bad because it would stretch space by, like I was saying, like hundreds of % right when it got close to us. And the black holes themselves would be about the size of LA. And so they would be effectively like tiny pinpricks, but, might be like 50 or 100 kilometers in size. And they would be able to, I don't think the Earth would get destroyed. However, so I can't say this with high confidence, but the Earth, again, using this, the Earth is a physically resonant system, and this thing has a quality factor of a few thousand, meaning it's just like a few thousand oscillations when I ring it. That's why it lasts for a second. So the Earth is like that also, except for the vibration frequency is about 30 millihertz, so 30 times once per 30 seconds. And so if the binary black hole pair came cruising through our solar system And right when it was coming through, if it happened to be going once per 30 seconds, yeah, it could excite the acoustic modes of the Earth. And
that would be bad.
It would be, it would like be bigger than the 9.5 earthquake in Chile, which happened in the early 60s and kept the Earth ringing for months. I don't know what would happen exactly, but I can imagine if we had it 10 times bigger than the world's biggest earthquake, it could hurt us in terms of earthquakes and tsunamis.
Yeah. Or we would find out what the inside of a black hole looks like if it got too close.
Yeah. All right, that's an interesting question and one I should compute. And
all right,
I will answer on Twitter.
Perfect. Okay, so we got one more then. This is from Margin Collector. Is the current method for detecting gravitational waves the best idea out there, or only the best practical way? Given the tech,
it is not the best idea out there. So there's in a number of ways. I mean, one way is making things longer, as people said. But what I gather from this question, I'm reading between the lines here. But is there some there's a good Elon Musk story where I think his analogy is like, we take New York City in the 1800s and it's all horses, and then we ask, what's going to happen to the output of all the horses once New York City scales to 20 million? Mm-hmm. You can't just scale everything by saying, well, we'll have more horses and we'll have so many more street sweepers or something. Eventually you shift to a new technology like cars. And so it's the same, like the normal answer I think people would give to, are we using the best technology, is, oh no, next year we're going to use double the laser power and a mirror that's even double.
Make it longer.
Yeah. But like in The Simpsons, they said, eventually these humans will make a board with a nail so big through it that they'll destroy themselves. So yeah, it's not the right way to go. If you ask in 100 years from now, will people still build Michelson laser interferometers and do the same thing?
Right.
I have a hard time believing that's true.
Right.
And one of the exciting possibilities out there, so there are ideas with using acoustic detectors and space detectors and using the timing of signals in space and so on. But in this frequency band, in the audio frequency band, I think me and some of the people who think about the quantum mechanics of this kind of detector have been thinking about how far are we, if you think about the pure mathematics of how information is propagated through space-time, like what's the information carrying capability in terms of number of bits of space? You have this much space, and how many bits can you send before space collapses on itself? And like with fiber optics, you have a limit to the number of bits you can send, which depends on your modulation bandwidth and the amount of laser power you can put in the fiber. And eventually, if you put too much laser power in there, you get stimulated Brion scattering from the glass and so on. And there's a kind of a bandwidth limit there, which is pretty high. It's plenty for YouTube, but it's still, there is a limit. And we have been thinking about the same kind of thing. And why aren't we doing better? Or where is all the signal to noise ratio going? When you think about the wave coming from outer space, we think probably the quantum fluctuations of space-time itself are probably at the Planck scale, which is 10 to the minus 34 meters. And the signal, like I said, is around 10 to the minus 18 or 19 or something. So there's a signal-to-noise ratio of 10 to the 14 or 15 there. And I'm telling you we're only getting tens. So there's a 10 to the 13 and the signal-to-noise is lost from converting from space-time to laser light. That doesn't seem like a good thing. There's got to be, since that's the biggest chunk of where we're losing it, we should be doing something better to transduce the space-time curvature into an electrical signal. And it might be that light is not the best thing. But even with light, we can do a lot better than what we're doing, and not just by making things heavier and doubling this or switching the colors or something. There's an idea which is called coherent quantum feedback. And that takes this takes this problem, I would guess, I would say, of the pressure from the light moving the mirrors around and turning it into an advantage. So like I described before, the beam pushes this thing and then this thing pushes back and that changes the light. Mm-hmm. Well, you can take this instability and essentially turning it into a system where quantum mechanically the mirror laser system has positive feedback, a lot like like an audio system. You've heard like when musicians practice sometimes, or I mean, it can be bad. So right when people have feedback, they're standing too close to the
like two mics next to each other type thing.
Exactly. But as we know from Jimi Hendrix, feedback can also be a wonderful thing, and he turned it into a fantastic thing from just an annoyance. So we'd like to do the same thing. So we'd like to take this mechanical, optical instability that comes from the laser system interacting with itself and turn the entire 4 kilometer plus 4 kilometer L-shaped thing into a unstable feedback system. So when the space-time fluctuation comes in, it excites this instability in our system, and then we detect the signals in a much stronger way. And so rather than think about it like the laser light goes and measures the space and comes back, it's almost like we have this 8 kilometer L-shaped laser tuning fork that picks up the space-time signal.
Right. So it's optimized for that one particular length, and so it just goes wild when it hears something.
Yeah, but in fact, I mean, you can optimize it for a single frequency, but the thing we've been thinking about just in the last month or two is how to make it optimum for a wideband. So we want to make a wideband unstable system.
To be determined.
Yeah. I think we have got 95% of the problem solved.
Oh, wow.
And on paper.
Okay.
But still, our aim is to try to build something like this year. And once we figure out how to do it, and
just like a scale model, you mean?
Yeah.
Or like you implement it at,
on the Caltech campus, we have a 40 meter size system.
Oh, okay.
And it's a 1/100th scale of the real LIGO detector. And we want to build this in. So we have little mirrors and little lasers, and they seem big to us, but they're really little. And we're going to build up this instability and see how sensitive we can become.
Very cool. Okay, cool. Thanks, man.